Right. So we are discussing chemical bonding, and last few sessions we were discussing in detail ionic compounds, right? And now we switch on toward the covalent bonding. Well, I'll be giving you the total details regarding covalent bonding. What actually the thing which we need to know prima facie when we switch from ionic bonding to covalent bonding. I wanted to present it to you. This is the basic issue why we don't have one single theory and you have several theories to explain what covalent bonding. What is the main thing? Remember that in ionic bonding, the bond between the oppositely charged ions is absolutely convincing. Why? Because observe, in ionic bonding you have electrostatic force, and this electrostatic force is binding the oppositely charged ions together. So if someone is asking me, where does the strength of the bond come in for ionic bond? I think I'm readily explaining that because you have oppositely charged ions, you have a positive charge, you have a negative charge, you have a cation, you have an anion, and naturally you will have an attractive force, and it's a strong force, that is electrostatic force, and that is when the strength of the bond is derived. That is where the strength of the bond is derived. So it's absolutely convincing of all the bonds which you propose, ionic, covalent, metallic, coordinate covalent, or whatever, induced bond or whatever. Right, out of all this, I think the ionic bond formation seems to be absolutely convincing. Absolutely convincing. The first thing is, if someone is asking this question, where does the strength of the bond come from? This is the question, this is the fundamental thing which one must answer. Well, this question is absolutely answered with highest degree of conviction in case of what? Ionic bond, because you can explain very clearly in ionic bond, you have a cation, you have an anion, and then you have in between them, you have an attractive force and a strong force which binds these two ions together, and the strength of the bond is derived from that. So hence ionic bond is a strong bond, right? Now the issue is when you switch to covalent bond, you have a perception towards it. If I ask a student who is studying high school, what exactly is a covalent bond, he would like to readily explain it to me, right? He says that you give one electron, I give one electron, we both put it at the center, the pair of electrons, and we both share. Right? In the process of sharing, what he might explain even better is both the atoms that are participate in bonding, they are achieving their octet, because our teachers were telling us that atoms participate in bonding because they don't have that octet configuration or something like that. This is what is you were told in school, right? That's all is fine. They achieve octet configuration. They say that when they achieve the noble gas configuration, they are stable. Fine, everything is fine. The narrative which is told in school is absolutely fine. I have no issues with that. But if I ask you a question in covalent bond, after you tell me this story that you give one, I give one, we both put it at the center, and then we both share these electrons. If this is the case, then if I ask you a question, where does the strength come from? Where does the strength of the bond coming from? If you explain to me that here is A, you give one electron, here is B, you give another electron, right? And we share. For example, if you have fluorine atoms, fluorine molecule, if you wanted to explain, fluorine belongs to the 7th group. So it has total of 7 electrons. So if you actually see one here, you can actually see the 6 electrons over here, one here, and you can actually see this is the 6 electrons and total 7 which I'm accounting for. Now what happens is the fluorine doesn't have an octet configuration. So if you ask a high school student, he will be telling why fluorine is participating in bonding, then he will tell that fluorine doesn't have an octet. Of course it doesn't have an octet because you have only 7 electrons. And if the other fluorine also doesn't have an octet, so both came together, what they are telling is you actually contribute 1 electron, I contribute electrons, and this both is shared by both of us, such that it is 2 and 6 is 8, and this is also 8. So both have attained electronic configuration 8 of the the 8 of the noble gas configurations, you must understand. The outermost shell has what? The noble gas configuration, you must understand. So this is fine. This is absolutely fine. I have no issues in this. right? I have absolutely no issues. But the point is, this story, this narrative is fine for understanding covalent bond. But I wanted to know that where does the strength come from? Where does the strength for the covalent bond is coming from? Understand, please understand this, please understand that, in case of ionic bond, here is A plus, here is B minus, you have opposite, you have an electrostatic force that binds to, and hence the strength is coming from the electrostatic force which prevails naturally between this cation and an anion. Such an explanation basically missing in case of what? Covalent bonding, you must understand. The only thing what people can tell you is basically this, right? Suppose if hydrogen molecule formation is asked to you, here is one electron of hydrogen, here is another electron of hydrogen, both are sharing, right? This is the sharing, and a hydrogen molecule is formed. Similarly, all of the diatomic molecules, whatever, they just share, right? And then a covalent bond is formed. But what is missing, which is critical for our understanding, is I wanted to again and again ask myself, and I wanted to reason with you that where does the strength of the bond coming from? Where is the strength of the bond coming from? You can explain double bonds, you can explain triple bonds, right? Whatever. You give one, I give one, we both share. We are not, the shared electrons are not leaving my shell, nor you are gaining anything. Remember that. The electrons which are actually being shared, they are not out of the shells of that particular atoms. They are just contributing it. They are not taking, no one is taking away. They are actually sharing it. The electron is retained in the respective shells. You must understand. It's not leaving. If it leaves, then I think you develop a positive charge and you develop a negative charge. That's nothing but again an ionic bond. So in this process of explaining covalent bond, well, the critical point is I wanted to ask myself n number of times before I get into some theories is basically where does the strength of the bond is coming from? Where does the strength come from? Like, the strength is basically in sciences, when you wanted to explain strengths, you must be speaking in energy terms. In energy terms, in thermodynamic terms, you must be explaining. So I wanted to propose a theory which for the first time was able to explain what? A covalent bond, right? So before I go there, I just wanted to give you a graph, very strange graph, it even surprises to me even now, right? Observe this graph, what is happening here. Watch carefully here. Watch carefully. If I draw, right, on the ordinate, if I draw some potential energy, right, on the ordinate, if I draw potential energy, right, then what is happening is, if two atomic systems are coming together to form a molecular system, right, two atoms combine to give you a molecule. Now what is strange and surprising to me is basically what both the atoms are approaching each other, and when they are approaching each other, they are vomiting energy. They are vomiting energy. When they vomit energy, the potential energy is basically decreasing when they are approaching one another, because there is a conducive atmosphere for bonding. Both have agreed each other, let's share and achieve octet and achieve what? Stability. And I was always telling you, whenever you speak of stability, you must be what? You must be explaining in terms of what? Energy, you must understand. So when two atomic systems are approaching each other for a bond formation, what happens is the energy of the system is coming down. And what surprises me, after some time, if you try to go close, if you go very close, rather than attraction, you have repulsions. Surprising, very surprising. So what I mean basically is, two atoms are approaching each other, yeah, they do approach. They wanted to come closer, in fact, they wanted to overlap or whatever, but they have the interest of coming together. When in the process of coming together, the energy is vomited and the potential energy is taking a dip. It takes a dip till certain extent where it reaches a threshold or a minimum potential energy. But if the atoms are trying to move very close to one another, then it's not a simple jump of potential energy, but rather an exponential jump of what? Exponential jump of what? Potential energy has been noticed. When you have an exponential jump of potential energy, one must understand as a science student that there might be what? Repulsions actually taking place rather than attractions. So we all started with attractions coming together, energy of the system is lost, and we are standing at a distance where you have the lowest dip in the potential energies, and thereby you actually have an exponential increase of potential energy, and that's where the repulsions are actually starting, you must understand. So this entire story, what I was telling to you, can be put as a pictorial representation, you must understand. Look into this. Here are two atoms. They are very far away. They are very far away, right? They are very far away. And then when they are approaching each other, as I said, this is the potential energy, right? This is the potential energy when they are approaching. They are far away rather. They are actually far away. These two atoms are actually far. And look into the potential energy. This is what is the potential energy, what they have. When they are very far away, right? When what happens is, when they approach each other, the potential energy takes a dip. The potential energy basically takes a dip. When it takes a dip, it will actually dip like this, dip like this, dip like this, dip like this, and you have a threshold. Remember that you have a threshold. You have a threshold here, right? It takes a minimum dip when they approach. You take a minimum dip like this, right? Minimum dip like this, and this is where the atoms are almost close to one another. Almost close to one another, and they stop at a distance, right? And what is noticeable, we wanted to know why they are not actually going and, overlap with one another to get too close to one another. If we speak in energy terms, after all, everything is energy terms in science, right? And the potential energy was this much when they are far away, and it's taking a beating down, down, down. It's actually dipping, right? This is the minimum what? That is the minimum thing. It doesn't dip further. It doesn't dip further. And then suddenly what happens is, if you go very close, then you have an exponential rise of what? Potential energy. You have an exponential rise of potential energy. And mind you, this is actually too much, almost overlapping with one another, which is not conducive. Remember that atoms combine to form molecules, and in the process, we must have minimum energy. After all, understand that stability is basically a function of energy. And if you wanted a relation, stability is inversely related to energy, you must understand. So when two atomic systems are combining together to form a molecular systems, the molecular system must have the lowest energy. And the lowest energy is actually here. So the atoms are approaching each other and they stop at a distance. And that distance, the internuclear distance when they stop where you have the minimum potential energy, that internuclear distance is basically nothing but the bond length. That's nothing but the bond length. So basically, if I say this internuclear distance when they stopped, this is actually referred to the bond length. You must understand, that's the bond length. And if you try to force them further, if they go close further, then you have not only increase in potential energy, but actually you can see there is an exponential increase. You have an exponential increase in what? Potential energy. And then you are not speaking of stability, because stability is inversely related toward energy. The lowest point in the potential energy graph, when a molecular system is formed, when atomic systems are combining, at that point, when they stop and there is no increase in potential energy, the lowest dip in that graph, when they stop overlapping, and that if you take an internuclear distance, and that can be called as what? Bond length, you must understand. Right? So at some point of time, they will stop. If someone is asking you, you get into an engineering college tomorrow, a professor is asking you, you started off with what? Dip in potential energy, and then if you're trying go close, at some point of time you stop. Why do you stop it? Why don't you go further? If that is the question, then you tell him that everything is explained in terms of energy terms, and the lowest dip is there, which the people stop, and if you go further, the potential energy is basically increasing, and then the stability is further decreasing. In fact, if this is actually creating what? Repulsions. This is basically, you started off with what? Attractions, and attraction is continuing, attraction is continuing, attraction is continuing, and this point is where you have maximum what? Attractions, maximum attractions you have, and further actually increase in what? Potential energy. You must understand that is the dynamics of how a covalent bond is formed. You must understand that, right? But we have not answered the question which we have raised. We have not answered the question what we have raised in the beginning, right? This is the energy diagram where the dip is the point where we measure what? Bond length, and that is where the system is what? Stable, right? The system is nowhere stable, rather not here, not here, not here. Here it is actually you have the stable what? System, and that's what is referred to be what? A bond length. You must understand that, right? Let's come back to our question, a critical question, right, which we need to answer. Observe carefully here. All fine, everything is fine, everything is good. So covalent bond, if someone is asking me here, but where this question is unanswered. Where does the covalent bond derive strength from? Where does the covalent bond derive strength from? This question we need to answer. These questions, these reasoning things have not cropped up when we are actually discussing electrovalent bond. In electrovalent bond, it is positive ion and it's a negative ion, and naturally you will have what? Electrostatic forces of attraction, and then it is all fine. It is all fine. And that is how the strength of the bond is derived, and no, everyone are convinced. In case of covalent bonding, it seems like a story. You tell people that the atoms are not having octets. We both share, we achieve octet. You give one, I give one. We both put it at the center. Live happily with a great stability. This is what is it's like looking like a story. But as I told, in sciences, whatever you explain, you must be doing it in energy terms. That's when we are more convinced, because anything that happens in sciences or in chemistry happens for stability, right? And for stability, in fact, stability is inversely related to what? Energy, you must understand. So all happens for stability. If this is the case, then how do we answer this? Where does the covalent bond derive strength from, right? And the first attempt was made by introducing the concept of overlapping, right? Observe carefully here. If you wanted to answer covalent bond strength derived from what? Derived from what? For this, I introduce the concept of overlapping. The concept of what? Overlapping. The concept of overlapping of what? Overlapping of orbitals. You must understand. Concept of overlapping of what? Orbitals. Now what is very strange, I want everyone's attention. See, if someone is asking me, how do you explain fluorine molecule formation? Then people are so complacent. Before the concept of overlapping was introduced, what people used to tell me is like this. Here is an atom of fluorine. Here is an atom of fluorine. They both overlap, and then a fluorine bond is formed. They tell you it's so complacency, in explaining fluorine molecules or chlorine. What they're telling me basically is a fluorine atom and the other fluorine atom are overlapping with one another. Or even if you wanted to explain hydrogen, they are telling me the hydrogen atom is approaching the other hydrogen atom and both the hydrogen atoms are overlapping. Ridiculous. Atoms overlapping is nonsense. It doesn't happen. It doesn't happen like that. Atoms don't overlap. They don't overlap at all. Now what is very strange, you know what is very strange is, it is basically, if I write the electronic configuration of fluorine, it is 1s2, 2s2, 2p5. And if I can split this, it is 1s2, 2s2, 2px2, 2py2, 2pz1. You should understand this, 2pz1. So while the formation of fluorine molecule, right, the atom constitutes all of this. But all of these are not overlapping. This doesn't have any role to play. The 1s has no role to play. The 2s has no role to play. The 2px2 has no role to play. The 2py has no role to play. It is the small 2pz, which is belonging to the outermost shell, is basically involved in overlapping, and hence the fluorine molecule is formed. So you seem to be absolutely silly. Before the introduction of overlapping, where you cannot explain where a covalent bond strength is derived from, you are not in a position to explain where the strength is derived from. People were complacent and they're telling, oh, obvious fluorine molecule formed. A fluorine atom is coming like this, the fluorine atom is coming like this, each fluorine atom overlaps with the other fluorine atom. Absolute nonsense, ridiculous nonsense. It's so micro in nature. This is basically so micro in nature, right? What is so micro in nature? Watch. This entire thing constitutes fluorine. And when the entire this constitutes in fluorine, this doesn't participate in bonding at all. It is not involving at all. Yeah, it might be influenced, but it is not participating in what? Any of the bonding. Neither overlapping, nor this, nor this. It is only this. Outermost, that too, outermost. It is basically the outermost small 2pz, which is basically inward bonding. It is not the fluorine atoms which are overlapping with one another, neither the hydrogen atoms which are overlapping with one another, nor any atoms that are participating in covalent bonding are actually what? Overlapping with one another, you must understand, right? So if this is the case, so let us have a theory in place. Let us have a theory in place to explain these micro things. So there are two things before us we must be clarifying. The first thing is, where does the strength come from? That's number one, which we need to answer in terms of energy terms. Second, it is not the atoms that are overlapping, it is only the orbitals, that belong to the outermost shell, which are actually participating in bonding, which we need to what? Explain, right? If this is the case, let's take the concept of overlapping. Observe carefully. So, to explain covalent bonding, I introduce the concept of overlapping. The concept of what? Overlapping, which is coming under the valence bond theory. Valence bond theory, and this for the first time is basically introduced by Linus Pauling. See, there are primary two things which are clarified in Linus Pauling theory, that is nothing but the concept of overlapping. First of all, the first thing what he clarifies, well, I would like to write the aim rather. You know, the aim of the concept of overlapping is, the aim is, in this theory, he will explain where does the strength of covalent bond come from. He will explain this. Where does the strength of the covalent bond come from? That's number one. Number two, what he will explain is, right, the concept of what? Overlapping of orbitals. It's orbitals, not atoms. It's not the atoms that are overlapping. It is the orbitals, the small, tiny, minuscule orbitals present in the outermost shell. They are actually responsible for what? The bonding, and not the atom as a whole. Silly. that you explain the two atoms are overlapped with one another. Ridiculous. Right? So if someone is asking you, what is there in valence bond theory proposed by Linus Pauling, you tell them that where does the strength of the covalent bond come from is what explained here. The second thing what he's explaining is it is not the atoms, but it is the orbitals that present in the outermost shell which are responsible for a bond formation which will hold these two atoms together. Let's get into details then, and here I present to you the postulate number 1. Watch carefully here. And what he's telling in the first postulate is this. A covalent bond is formed by overlapping of atomic orbitals. Look into this. He says, if you ask, and this must be carried by you forever. This seems to be the best definition available for covalent bonding. Don't forget about the story what you were told in school. That's fine for our understanding and creating a perception. But you can't be judgmental with that particular narrative what you were told in school. So the best way to explain covalent bonding is formed by overlapping of what? Atomic orbitals. It's formed by overlapping of atomic orbitals. Right? Now what do you mean by atomic orbitals? Look into this. Look into this. And now atomic orbitals, what are they? These are S, P, D and F. S, P, D and F. These are the atomic orbitals what he is speaking. Then the permutations and combinations, if you actually see, when you have S, P, D, F, they look like this. Watch. Then what he is telling is, you can have an SS overlap. You can have an S and S overlap. You can actually have an S and P overlap. Or you can have the P and P overlap. You can have P and P overlap. Must understand. You have S and S, P and P, right? Or S and P overlaps. Now the first thing is, first of all, this is first time introduced, please understand. The overlapping of atomic orbitals, how is actually energy-wise it is feasible. How is it feasible energy-wise? Let's understand. Now suppose if I take an SS overlap. Watch carefully here. If I can explain SS overlap, right? Here is an S orbital. This is an S orbital. This is no atom. This is no atom, please. This is no atom. Atoms overlapping with atoms is ridiculous. Don't do that. Don't explain that way at all. Divorce it. I'm speaking of an S orbital in a particular atom. An atom can contain S, P, D, F, so many. But this I'm speaking of an S orbital that is belonging to the outermost shell and which has an unpaired electron. So be clear. When this is S orbital and you have an electron here. Now what is happening to this electron? What is happening to this electron is, this electron is revolving in this particular area. In that particular area itself, in that atom, the S electron. Now I have another. You have an electron which is revolving only in this area. So it's basically revolving like this electron. This is how it is doing. So that electron is localized. Look into the terminology what I'm using. The electron in one S orbital is localized toward that small area. And the other electron in the S orbital is localized and it's revolving dynamically only in that particular area. Right? Now what I'm proposing is overlap. So first of all, why overlapping? Now what I'm explaining basically is the concept of overlapping which he is proposing is thermodynamically feasible, energy-wise feasible. It's basically energy-wise feasible. So whatever you propose, you must be linking it to energy, because after all, what happens in chemistry, what happens in science is basically for stability, and stability must be always explained in terms of energy. So when you are introducing the concept of overlapping, the concept of overlapping must be feasible in energy terms. So that's what I'm explaining here. So if I take a particular example of an SS overlap, you must tell us that SS overlap is done for a purpose. And what is the purpose? Well, I'm happy in this s orbital I'm revolving in a particular area. And I'm also happy that this electron is moving in a particular area, so they are localized to that particular areas. An electron is a dynamic particle, it's moving here and there, so I think it is localized here, it's localized here, it's localized, and it's moving. It's a dynamic particle with a speed of 10 power 8 centimeters per second approximately. Now when they overlap, this is how they do. Look into this. When they overlap, like this is an SS overlap. And finally, this is what they get. That's what they get. That's what they get, a larger area. Earlier I was just localized toward this particular area. And now I was localized to that particular. It's almost like you are localized to this room. If I ask you to roam in this room, you will be rotating in this room forever. Now if I ask you go and even rotate in the next room to that, then you are getting a larger area to roam. Then you're getting a larger area and the electron is dynamic and is now moving in a larger area. And look at this. This is an atomic orbital. This is an atomic orbital, AO. AO is an atomic orbital. And here the electrons are localized to a particular area. Now what happens is when they overlapped, this is called a molecular orbital. This is a molecular orbital. And the molecular orbital is having a larger area compared to the atomic orbitals. So now what is happening? The electrons which were earlier localized to a particular area are now moving in a larger area. If I ask you to move in one room, you're moving in one room. You're losing some energy. They are losing some energy. But if I ask you to go, combine with the next room and now move, I think you are moving in a larger area. Then you lose more energy. Well, the moment the concept of overlapping was introduced, it is feasible as far as the energy terms are concerned, because atomic orbitals forming molecular orbitals is absolutely feasible in energy terms. So look into this. This is an atomic system. This is an atomic system. When you go for an SS overlap, this is the final structure what you're getting. And the molecular system, I think the electrons are moving in a larger area. That's what I call it to be delocalized. It's basically delocalization. You're localized here. You're localized here. Now basically you're delocalized. When you're basically delocalized, delocalization always results in loss of energy. So hence I say a delocalized molecular orbital seem to be having a lower energy compared to the atomic orbitals. And a lower energy system is absolutely stable. So someone proposing a concept of overlapping, well, I accept it by default because it is energy-wise feasible. It is energy-wise feasible. For example, if you look into this, if you look into these, all these overlaps, so this is S and S, and finally you get this, right? This is an atomic system, atomic orbital, and this is now a molecular orbital, and that is an SS overlap. This is SS overlap, right? And the molecular orbital system seem to be much stabler because now the electron is basically delocalized, right? And if I take an SP overlap, if you look into the SP overlap, this is an S orbital, AO, S atomic orbital, and you have this P. This is the P atomic orbital, and now both are localized. The electrons are now localized in S and the electrons are localized in what? P. But when they try to overlap, then this is what is the result, what I can say. This is a molecular orbital as a result of SP overlap. As a result of what? SP overlap, you must understand. And then if you have PP overlap, this is PP overlap, right? And you have a p orbital, you have a p orbital, they are localized now. When you delocalize, it is what? You get like this, as if it is a chocolate. That is a molecular orbital. So a molecular orbital system seems to be more stabler than the atomic orbital system when they overlap. So two things is in my mind now. Two things are in my mind. Number one, understand that it is not the atoms that are overlapping to form a covalent bond. It's not the atoms. You cannot be so silly. How is fluorine molecule formed? Fluorine atom comes here, fluorine atoms comes there, and each atom overlapping with the other. Ridiculous, nonsense, silly, trivial. That understanding must be junked. And of course it is a junk after the concept of overlapping was proposed. Because in concept of overlapping, what is happening is, we were able to explain in energy terms, in thermodynamic terms, right? Because when you overlap, you are delocalized. Earlier, I am just belonging to my city. Now I am belonging to my country. Now I am delocalized towards the entire country. So I am roaming around all the country and roaming around in a particular city and then roaming around a country. I think you're delocalized. In the second case, I think you're losing more energy. So delocalization always results in what? Loss of energy. So the concept of overlapping is embraced because it gives us energy-wise stability, that is energy feasible stability. You must understand that. Right? So that is number one. So coming back to the postulates, watch carefully here. This is what he wanted to say. The first postulate. A covalent bond formed by overlapping of atomic orbitals. Overlapping of atomic orbitals. And then what happens is you have several types of overlappings. Types of overlappings. The SS overlap, which looks like this, and this SS overlap looking like this, and finally the final orbital somewhat looks like this. This is the s orbital, this is the s orbital, and this is now a molecular orbital. You must understand, that is a consequent orbital. You must understand this. And then if you have sp, this is the s, this is the s orbital, this is the p which is having a dumbbell, and when they overlap, this is how they look. And finally the consequence is somewhat like this. This is the molecular orbital of sp overlap. sp overlap. Now remember, the ss overlap, this is considered to be a head and head. And this is head-on overlap, what we call. This is head-on. Head and head, there is absolutely no tail. Right, is head-on overlap. And in sp also, this is a head, this is a head. So this is also head-on. Right, that is an sp overlap. Then you have a pp overlap. In pp overlap, well, I would like to draw like this, observe, because p orbital is, you know, in p orbitals, you have px, py, and pz. Both, all the three are mutually perpendicular. So when you are telling pp overlap, then you will have two types. What are the two types? Observe. Observe carefully here. Now the pp orbital looks like this. The pp orbitals, right, this can be a head-on or even sidewise, because you don't have a single p orbitals. You have px, py, and pz. This is the px, this is the py, and this is the pz. You must understand. This is the px, py, and pz. And they are basically mutually perpendicular. They are mutually perpendicular. So when I say pp orbital, I'm not taking a particular p, because the p subshell is divided into three orbitals, px, py, and pz. I've drawn all, right? And then if you take the another set of p orbitals considered for overlapping, this is px, that's py, and this is pz. This is px, py, and this is pz. You must understand, that's pz. Now what I'm telling is, whenever there is a pp overlapping, it will be two types happening. One is the head-on. This is the head-on which I'm speaking of. This is the head-on. This is the head-on. And once one head-on is involved, the remaining two will be sidewise, that is parallel. Right? These two are parallel. Look into this. These two are parallel. This is the sidewise overlap which I'm speaking of. Right? Similarly, this and this are parallel. Right? So you have this and this going what? Sidewise, you must understand. So where p orbitals can be two types, one a head-on overlap and the other is what? Sidewise. That's what I'm writing, head-on and sidewise. This is the head-on overlap and these two will be what? Sidewise, because x, y, z are mutually perpendicular and they are not isolated, you must understand. So these are the types of overlapping. So two things which are very clear. Why I embrace the concept of overlapping is it is energy-wise feasible, right? So you understand this is the first postulate what he is telling. Watch carefully here, right? So the very first point, the valence bond theory. The valence bond theory. The very first point what he's telling is a covalent bond is formed by overlapping of atomic orbitals. The covalent bond is formed by overlapping of what? Atomic orbitals, you must understand, right? So the concept of overlapping was first introduced by what? Linus Pauling. Now what we will do, well, beforehand I would like to tell you or warn you rather, even though we are embracing by difficulty, by default, that you know the concept of overlapping is the best to explain what covalent bonding. Remember, the most common thing what we all have is demerits. Every fellow has what? Demerits, which I would like to say, even though we are running through the beautiful narrative of the concept of what? The overlapping, because it's energy-wise stable, but I think this fellow also has what? Some of the demerits, which we will list it out. The first, let's take the merits and let us explain these examples. Now look into this. Look into this. Formation of hydrogen molecule, beautifully explained. If anyone has beautifully explained this, it is of course what? Linus Pauling. It is so beautiful to watch. Earlier, if someone is asking how hydrogen molecule is formed, hydrogen is coming from this side, hydrogen is coming from this side, both the atoms overlap and then hydrogen bond is formed. This is ridiculous, right? But look into the beauty of this theory. Look into this. How is this formed? Hydrogen electronic configuration, if I write, it is 1s1. So if you wanted to describe it, it looks like this. Look into this. This is 1s of hydrogen atom. And you have one electron here. One electron over there. Right? I have one other hydrogen. So you have hydrogen with one electron. That's what I'm representing it. So this is 1s of hydrogen atom. This is an atomic orbital. Right, you have another hydrogen atom, same 1s of another hydrogen atom, and this is nothing but the atomic orbital, but this time opposite spin. Well, one of the postulates of Linus Pauling says, only those orbitals, not every orbital. So this narrative, which was prevailing before the concept of overlapping, that every fellow participates in bonding, the entire atom is overlapping with another atom, is ridiculous, nonsense, silly, trivial. Not every orbital will be overlapping with one another. No, absolutely not. It doesn't happen. Only those orbitals in which the electrons possess opposite spin shall be going into what? The bonding, the overlapping. So, I would like to highlight this point also. I would like to say only those atomic orbitals in which electrons possess opposite spin participate in bonding. Only those atomic orbitals in which the electrons possess opposite spin only participate in bonding. No other fellow is touched. No other fellow is touched. So your argument that how fluorine molecule or hydrogen molecule is formed, atoms overlapping with one another, every electron in the atom is participating in bonding, is ridiculous. So there is a condition. Only those electrons, those unpaired electrons which possess opposite spin only participates in bonding. So very consciously, I am drawing these atomic orbitals with opposite spin. It's not my wish and my choice or forgot, I'm not conscious or something like that. It is absolutely not like that. There are some rules, right? So this is a clockwise, anti-clockwise. Only these two overlap, and that overlapping, I'm showing you this for you. This is the SS overlap. That is the SS overlap, right? And if I can show this in diagram, then it gives rise to this one. These are the bond pair now, right? And if I can show this to you in pictorial representation, this is the 1s. This, I'm speaking of hydrogen molecule. This is the 1s. You have an electron here. And then you have the another 1s of the hydrogen, which has an opposite spin. They both overlap, and it looks like this. So these two, one is AO of hydrogen, one is the atomic orbital of hydrogen, and here is a bond. So what is happening basically is, this bond is this is what is shown as the hydrogen molecule, you must understand. And remember, it's a head-on overlap. This is a head and head, which is basically head-on overlap, and which results in a strong bond called sigma bond. So the single bond, what you're seeing here, is basically a sigma bond, you must understand. It's basically a sigma bond. So head-on overlapping always results in what? Sigma bond, and that's how beautifully explained. Now what is beauty? You might ask me, what is the beauty here? Is the same thing explained earlier also. When there was no concept of overlapping, also we explained the hydrogen atom. Remember, the basic difference is, remember that this is not hydrogen atom, man. This is not hydrogen atom. It is the 1s orbital in hydrogen atom. And this is the 1s orbital in what? Hydrogen atom. And the condition is only those orbitals in which electrons possess opposite spin will only participate in bonding. This is better explained if we actually take the second example, right? Observe carefully here. So beautifully explained. What we will do, we take the formation. Let us explain the formation of chlorine molecule. See, one thing one must understand, I'm not preparing molecules here or, I'm not preparing anything. I'm not preparing anything here. So have this thinking, I'm not preparing absolutely anything here. Molecules are already formed in the lab. They are existing. Fluorine molecule exists, chlorine molecule exists, HCl exists, everything exists. All the molecules are formed. What I'm doing here is, I'm just reconciling how the bonds are formed. Can you give any explanation? Explanation to the bonds formed has been given in this class. In the classroom, I'm not preparing any molecules here. Molecules are already there. The bonds explanation, how are they formed? We are giving a theory because a practical thing must be backed by a theory, you must understand. If this is the case, the best one to explain is formation of chlorine molecule. So what I will do, the chlorine is 17. So if I write its electronic configuration, it's 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, and 3pz1. Well, as a chemist, you and me must have a habit of underlining the outermost shell, because in chemistry, the outermost shell is extremely important. The outermost shell is extremely what? Important. You must understand. So the outermost shell seems to be the number 3. That is the outermost shell, and if I can write it, the entire outermost shell is the third one. This is 3s. Watch carefully here. 3s, This 3s, this is the outermost shell, that is the 3s, and you have 2 electrons here paired, right? It is paired. Then I come to what? The 3p. This is the 3px. This is the 3py. This is the 3pz. And in this 3p, I have 2 plus 2 plus 1, 5 electrons. In the p subshell, you have 5 electrons, and we have to follow Hund's rule. So what you are supposed to do, you start off first singly 1, 2, and 3. Once this is half filled, the pairing starts. You must understand. Look into this. This is 4 and 5. And now the unpaired electron is clearly visible to you. It's important to quote the unpaired electron because only those orbitals in which the electrons possess opposite spin will only participate in bonding. Now, what is very strange, first of all, I didn't consider this. No. And I am considering the outermost shell, in which also this is paired, this is paired, this is paired, and that is unpaired. Then ask me, why did you write? If you ask me, why did you write then? Well, outermost shell is the one which is getting most influence, so I give importance to the outermost shell, hence I have drawn. Similarly, this is one chlorine atom. This is one chlorine atom. Similarly, let's draw the another chlorine atom because 2 chlorine atoms form a molecule. So if I can draw, watch. This is the 3s. So again you have 2 electrons. This is the 3px, 3py, and the 3pz, in which I need to fill 5 electrons. But I'll be careful because you must have opposite spin, right? So what you do is you start off like this: 1, 2, 3, and 4, and 5. And look into this. This one has a clockwise spin. This has an anti-clockwise spin. And according to valence bond theory, only those orbitals will be overlapping in which the electron possesses opposite spin. Not every electron is involved in bonding. That is the beauty of what? Valence bond theory. If you ask earlier, how is a chlorine molecule formed? That fellow will tell you the chlorine atom is coming from this side, chlorine atom is coming from this side. They both overlap with one another. Atoms don't overlap. It's not atoms that are overlapping. In the atoms, only those orbitals in which the electrons possess opposite spin. In fact, not every electron is actually participating in bonding. That is a critical point of this theory. So now you have the opposite spins. Only these will overlap. And this 1p orbital, 3pz and 3pz, head on p and p. That's what is overlapping. This is not participating. All these are they're just spectators. They might get influence, that we will consider later in a theory. They might be getting influence because when 2 atoms are approaching each other, every electron gets influenced. Whether we consider or not is that's a separate discussion which we will make. But at least for participation in the bonding, it is only those orbitals which possess what? Opposite spin will be doing it. And if I can draw the pictorial representation of this, then it looks like this. Look into this. This is the 3pz of chlorine atom. That is atomic orbital. This is what I have drawn, the 3pz, which has a dumbbell shape. This is the 3pz of one chlorine atom, in which you have an electron which is having this spin clockwise. And this is now overlapping with another p orbital with an opposite spin. This is the 3pz of another chlorine atom, then this is the atomic orbital. Now what happens when these two overlap like this? This is head on, so that is pp head on. pp head on, and the result will look like this. This overlapping, the result will somewhat look like this. Watch. Look into this. What is very strange, in such a big chlorine atom, it is a small, tiny 3pz. which is holding these two chlorine atoms together. The chlorine atoms are not overlapping. It's this tiny 3pZ and the tiny 3pZ which is actually holding these two chlorine atoms together, and this will result in the formation of Cl and Cl. You must understand. So, if you wanted to explain this chlorine bond, how is it formed, don't tell people that chlorine has overlapped with chlorine. No, it doesn't happen like that. It doesn't happen like that. It is the 3pZ and the 3pZ of this chlorine atom, they overlap and form a sigma bond. And the other electrons are here. The 3s, the 3px2, 3py2, the 3s, 3px2, 3py2, they are just looking like that. And it is only the 3pZ which is overlapping, and this is the 3pZ which is holding this chlorine atom and this chlorine atom together. So at the micro level, explanation is given by what? The valence bond theory. So look at the beautiful explanation. No other theory can explain the formation of fluorine or chlorine or hydrogen molecules than done by valence bond theory, you must understand. So beautiful. So beautiful. So how chlorine atom is formed, if someone is asking, it is not the atoms. It is not the atoms, you must understand. It is the orbitals which are actually involving in what? Bonding.